Welcome to the new topic on nuclear physics. So in this video lesson we are going to revise what should have been taught to you in grade 10, the basics of nuclear structure. So we're going to look at distinguishing between the nucleon number or the mass number and the proton number or the atomic number. We're also going to look at understanding that an element can exist in various isotopic forms. So that would be isotopes of a particular element, and then we are going to look at using the usual notation for representing nuclides of X, A and Z. So nuclear physics is one of those topics that people immediately think of as being only for the super smart. And while nuclear physics can be, and certainly does have aspects of it that are very challenging to understand, in this topic, or in this module, we're going to look at how accessible nuclear physics is to secondary students. So nuclear physics studies the properties and behavior of atomic nuclei and how these nuclei are created. This is also going to link to the section or topic that follows after this section on nuclear physics, namely cosmology. So every natural element found on Earth was created by nuclear processes in stars. So this is referred to as stellar evolution or nucleosynthesis. Nuclear physics plays a pivotal role in a wide variety of applications, from medical imaging. I'm sure you've heard of nuclear magnetic resonance or NMR imaging, and cancer treatments, so for instance radiotherapy, to radioactive dating of materials. For instance, in anthropology and in paleontology they use dating techniques like, for instance, carbon-14 dating, as well as energy generation, for instance in fission reactors like at the Coburg power plant. So nuclear physics is a fascinating topic, and we are going to now start delving deeper into it. So let's start off with some definitions. So the proton number is the number of protons in an atom, and is also referred to as the atomic number, and the symbol is a capital Z. So the atomic number is what actually determines what type of element the nucleus is actually found in. The nucleon number is the number of protons and neutrons in the nucleus of an atom. Remember, a nucleon is a general term for particles that are found in a nucleus, so that includes protons and neutrons. Because of the fact that the nucleus is so heavy in comparison to the electrons, we say that the mass of an atom is actually found, 99.99999% of it is found in the nucleus. So we refer to the number of nucleons in a nucleus as the mass number, and we use the symbol A. So just to reiterate, the nucleon number is the proton number plus the number of neutrons. Therefore, the number of neutrons is equal to the nucleon number minus the proton number. In other words, the mass number minus the atomic number. And the number of electrons is equal to the proton number or the atomic number when atoms are neutral. So in nuclear physics we represent a nuclear species or nuclide as follows. We use the X, which is the chemical symbol of the element that you find on the periodic table. Then the nucleon number is the bigger of the two numbers. It's the A, and the atomic number is the Z, and the Z is less than or equal to the A. So for instance, in hydrogen, you get that the nucleon number is 1 because there's one proton in the nucleus, but there's also only one proton, so it's 1 and 1. But for instance, in helium, it would be 4 and 2. So when we look at the periodic table, we always look to see which one is bigger. Sometimes, like the periodic table we use, is the nucleon number actually sits at the bottom and the atomic number sits at the top. So you must always just check when you're using a periodic table what the convention is that they are using. So let's look at an example of fluorine 19,9. So here we can see that the mass number is on the top, or the nucleon number, and the atomic number or the proton number is at the bottom. So Z equals 9, which implies that there are 9 protons in the nucleus. The mass number is 19, so that's the number of neutrons plus protons equals 19, but the protons, there are 9 of them, so subtract 9 and we get that the neutrons is equal to 10. If we're dealing with an atom, then an atom is neutral. In other words, the number of protons equals the number of neutrons. Then the electron will equal the atomic number as well. But one must be careful with this, because as soon as we start to deal with ions, then ions are formed by the transfer of electrons. So if it's a positive ion, the amount of electrons will be less than the atomic number. And if it's a negative ion, then the amount of electrons will be more than the atomic number. So just to revise, if we have a nuclide, in other words, we have a nuclear species where the mass number is A and the atomic number is Z, then the protons, the number of protons equals Z, and the number of neutrons is the difference between the A and the Z. Now just be careful, A does not stand for atomic number. Sometimes learners get mixed up. The A stands for mass number and the Z represents the atomic number. In nuclear physics, isotopes are a very important concept. Now, an isotope is atoms of the same element with different mass numbers. In other words, different number of neutrons. So that is key. If atoms come from the same element, their atomic number will be the same. In other words, their proton number will be the same. But depending upon the amount of neutrons that there are in the nucleus will determine what isotope it is. Remember the Greek word isos means equal. So for instance, an isosceles triangle is a triangle with 2 equal sides. So isotope means same element but different mass numbers, different number of neutrons. So when it comes to isotopes, we normally use the name or the symbol of the element, a hyphen, and then we use the number, the mass number, or the nucleon number. So for instance, this would be protium, which is the normal hydrogen. It's 1 proton, 1 electron. Deuterium is 1 proton, 1 neutron with an electron. So that's deuterium. It's H2 because there are 2 nucleons in the nucleus. And then we have H3, which is tritium, and that we have 2 neutrons and 1 proton and 1 electron, and so that is a heavy isotope of hydrogen. Note that each of the hydrogens has only 1 proton. That's what makes the atom, makes the nucleus a nucleus of a hydrogen atom, but the number of neutrons differ. So being more explicit about it, so hydrogen 1 would be 1 hydrogen, so the number of protons is 1, the number of neutrons is 1 minus 1, which is 0. Hydrogen 2, the mass number is 2, the atomic number is 1, so the neutrons will be 2 minus 1, which is 1, and with hydrogen 3, it's 3 hydrogen 1, protons is 1, neutrons is 3 minus 1, which equals 2. So notice all the protons, all the isotopes have the same number of protons. That's why they're isotopes, because they're all nuclei or atoms from the same atom, and the neutrons differ. So in nuclear physics, our focus is on the nucleus. So sometimes we will ignore the atom and just talk about the nucleus, but in a natural state, nuclei are found in atoms. So when it comes to carbon, carbon has actually has 3 isotopes, carbon 12, carbon 13, and carbon 14. We'll look at that in more detail just now. But carbon 14 is quite well known because carbon 14 dating is used to determine ancient artifacts up to about 50,000 years old. Beyond that, they use other dating techniques There's often been debate about carbon-14 dating because of the fact that it's been affected by carbon-14 being spewed into the atmosphere during the 1950s and 60s when they did a lot of atomic bomb testing. And that increased the amount of carbon-14 in our atmosphere. So carbon-12 would have 6 protons and 6 neutrons, because 12 minus 6 gives us 6. And carbon-14 would have 6 protons, but it would have 8 neutrons, because 14 minus 6 gives us 8. Remember, carbon is 6 protons, the atomic number is 6, that makes it carbon, and obviously the mass number determines what isotope we are dealing with. Note that isotopes of the same element have identical chemical properties, and that's because they have the same amount of electrons. Remember, chemistry, for the most part, the way substances bond, is based on the electron structure, and in particular the valence electron structure. So for different isotopes of the same element, the amount of electrons would be the same in neutral atoms. So the chemical properties would be the same, but the physical properties can be different based on how heavy the nucleus of the atom is. So the isotopes also provide evidence of the existence of neutrons in the nucleus of atoms, because that's the reason why the atoms have got different mass between the isotopes. So just to be explicit about it, for instance, hydrogen 1 proton, 1 electron, and we see that if it's found in water, when it reacts with oxygen, it forms water where the hydrogen has got just 1 proton in the nucleus. Then you start to get what we call heavy water, which is used in nuclear processes. And heavy water consists of H2O with 2 hydrogens, but where the hydrogens have got heavier nuclei than the more abundant hydrogen 1. So this is used extensively in the production of nuclear energy. So this is the periodic table we use in this course, and just to draw your attention to the fact that the atomic number is now sitting at the top and the mass number sits at the bottom. But what's interesting is some of the elements have got mass numbers that are not whole numbers. Now, in actual fact, all the elements have got mass numbers that are not whole numbers. Now, that sounds like it's contradictory. So if we look here, for instance, at copper and chlorine, we see that copper is 63.5 and chlorine is 35.5. Now, that doesn't make sense. Surely you can't get half a neutron. Well, you can't get half a neutron, because remember when we did quarks, you can't, even though neutrons are made up of 3 quarks, you can't split them. You can't separate them. So what this is an indication of the fact that what's sitting on this table is in actual fact an average, it's a weighted average of the different isotopes mass numbers that we find in nature. We are going to look into more detail into this soon enough. So here's the first example. We have got the various isotopes of carbon. We have carbon-12, which is stable. We have carbon-13, which is stable. And then we have carbon-14, which is unstable. Now, we'll learn later on when we do radioactivity, there comes a point where when you have a very heavy nucleus, that it starts to become unstable, and then it starts to, radioactive processes start to take place, which break down the nucleus naturally. But now we're going to look at what we call the abundance of carbon isotopes in nature. So if we had to take a sample of carbon, a large sample of carbon, and we had to use a mass spectrometer which splits up carbon into its different masses, we would find that in a large sample, 98.89% of the carbon atoms would have a mass of 12, whereas only 1,11% would have a mass number of 13. So we can see that most of the carbon in a sample from nature would be carbon 12. And only a tiny percentage of 1/10 to the 10 to the 12th would be carbon 14. So we can see this is minuscule in comparison to these two isotopes of carbon. Now we're being asked to calculate the average relative atomic mass. So we're being asked to calculate the weighted average of these isotopes in nature. So we write down the relative atomic mass of carbon is equal to 98.89% of all carbon multiplied by the mass number of carbon 12, which is 12, plus 1,11% over 100 multiplied by the mass number of that isotope, 13. And we view the amount of carbon 14 as negligible in this calculation because it's of the order of 10 to the minus 12 of a percent. So we can neglect that for the purposes of this calculation. So when we work each of these out, we get 11,8668 plus 0,1443, and this equals 12,0111. So this is the relative mass of carbon as we find it in nature. Now obviously you don't get a 0,0111 of a neutron, but this is a weighted average. So we're going to learn a little bit later, actually in the next video lesson, about atomic mass units. And so we will learn a little bit more about what the relative mass actually means. But for the time being, we can say that, like for instance, your shoe size would be a shoe size 10. 10 what? What's the unit? Well, it doesn't actually have a unit. It's relative to a size 1. So what is size 1? Well, we could use hydrogen, but in actual fact, it's relative to 1/12 of a carbon 12 atom. And that's 1 atomic mass unit. You should have learnt about this in grade 10, but we will revise it later on. So there is no unit here, but this 0.0111 is an indicator that we've been working with a weighted average of all carbon isotopes that occur naturally in nature. We have used this also when working with molar masses in chemistry. So here's an exercise for you. Calculate the relative atomic mass of rubidium, where in a sample of 100 atoms, 77 have a relative atomic mass of 85, while 23 have a relative atomic mass of 87. So pause the video here and try and solve this problem. So the relative atomic mass of rubidium, the percentage abundance in nature is 77 over 100, in other words 77%, multiplied by the relative atomic mass of that type of isotope, so this would be rubidium 85, plus 23% abundance multiplied by the relative atomic mass of that isotope, which would be rubidium 87. And we get a value of 85,46 for the relative atomic mass of rubidium in nature. Now give this one a try. Boron exists in two isotopic forms, B10 and B11. The average relative mass number of boron in the periodic table is given as 10,81. Determine the abundance expressed as percentage of the two isotopes of boron. So this is a reverse problem. We love to give these problems in exams. So I would like you to please pause the video here, give it a try, and then I will show you the solution once you've done. So we start off by letting X equal the percentage abundance of the boron 10 isotope. Hence, 100 minus X will be the percentage abundance of boron 11, because the two isotopes, their relative abundances must add up to 100%. So So we write down the equation. The relative atomic mass equals the percentage abundance of boron 10 multiplied by the relative mass, which is 10 for boron 10, plus the percentage abundance of boron 11, which is 100 minus x over 100, multiplied by the relative mass of boron 11. We now substitute for the relative atomic mass 10.81 equaling, now note the 10 times x is 10x over 100, multiply the 11 through, so 11 times 100 is 1100, minus 11 times x is 11x, all over 100. We now multiply both sides by 100 to get rid of these denominators of 100, so we get 10,81 multiplied by 100 gives us 1081, which equals 10x plus 1100 minus 11x. So we take the 1100 to that side, change the sign, so 1081 minus 1100 gives us minus 19 equals 10x minus 11x gives us negative 1x. Multiplying by negative 1 on both sides or dividing by negative 1 on both sides gives us that x equals 19. Therefore, 100 minus x will be 100 minus 19, which gives us 81. So the percentage abundance of boron 10 is 19%, and the percentage abundance of boron 11 is 81%. So we have now calculated the average mass of isotopes in nature, what we would call a weighted average, and then we've also looked at a reverse problem. So we have now laid a good foundation for what lies ahead as we move forward into radioactive processes.